shall next discuss minimization of DFA. Given a regular language, one can construct a direct DFA. Often, what we obtain may not be minimum. And when we were looking at a couple of case studies, we devised a strategy. We said, look at base strings. Keeping base strings as the pattern, we construct an automaton for base string, and then we start adding remaining transitions to complete the automaton. This was one approach, and with that we had kind of an intuition that for base strings you need this many strings, and we have not introduced new states, and with that we were able to manage other transitions. So with that we had an intuition that what we obtained was really a minimum deterministic finite automaton. And we had other approaches as well. For example, given a regular language, one can construct an NFA with epsilon and then go for an approach which will give you NFA without epsilon, subsequently go for subset construction. And we also looked at a couple of examples through which we saw that what we obtain through subset construction need not contain minimum number of states. And we also know that for a given regular language, one can come up with many different deterministic finite automata. So given all this picture, it is natural to ask, can we devise a procedure or can we come up with an algorithm which will give us minimum state deterministic finite automaton and given some arbitrary DFA. And so that's the objective of today's discussion. So before we get into the details of algorithm and so on, let's look at the picture. So we are given some DFA. So it has got a start state, and there are a couple of say accept states, and there may be some intermediate states. Maybe from this we come over here, then we may reach here, then we may loop on this, so something like this. Now the idea is the following. We are going to group into two blocks, or we are going to partition Q into final states and non-final states. Okay. Now our idea is the following. You keep this as one state in your ultimate minimum DFA. You keep one more state for final. Okay, let's assume this will become our ultimate final state. Our non-final state will be the start state. Now, with respect to this, we try defining the transition for each symbol in sigma. Now, it may so happen that on reading a symbol, say 0, you may get a transition like this. Meaning, one transition says you come back to a non-final state, another transition says you go to a final state. Because now you have grouped, given this deterministic finite automaton, and now that you have grouped, now things like this can happen. Okay. So on reading a 0, you get to see that because there may be one final state here, maybe say Q1. Q1 will say Q1 on 0 is Q1. Then Q3 on 0 may tell you it is Q4. Q4 is present here. Since Q1 and Q3 are in the same block, you will have a self loop at this place. Okay, so now what we will do, and from this we will split this into two, or meaning we create two sub-partitions. So this non-final states will be split into non-final state 1, non-final state 2, and followed by set of final states. Now we ask, if I operate on 0 and 1, is the transitions are uniquely defined? Meaning when I operate on 0, maybe I loop on n of 1, and when I operate on 1, I go to this. Similarly, when I read 0, I stay here. When I read 1, I go over here. And for 0 and 1, I stay here. Let's assume this is our picture. Now it's clear that for each state in this automaton, and the transitions are unique. On reading a symbol, we go to exactly one state. Okay. Now we stop and we say that from this say 5-state automaton, we have obtained a 3-state automaton, and this cannot be split any further. And if this can be split further, we could have gone for it. And this is the automaton in which you get to see that for each of them the transition is uniquely defined. Therefore, it is a minimum DFA. Why it is minimum? The ultimate minimum will have this 2 states, assuming there are non-final and final. Otherwise, you will have just 1-state automaton. And because this was not minimum, the next minimum is 3. So we try this. And once this satisfies deterministic property, we stop here. Therefore, because we incrementally build the automaton, when we stop, what we obtain is a minimum deterministic finite automaton. Okay, so the overall approach is the following. We group non-final and final, and with respect to non-final, you define transitions for each input symbol. Just like the way we define, you have set of states, and we define delta of say Q1, Q2, Q3, comma 0. We say operate on Q1, union operate on Q2, operate on Q3. On the similar line, define for this as well. Now we check whether after defining zeros and ones, whether for each of them the transitions are uniquely defined. If yes, then we stop and we say this is our minimum DFA. If not, you will find that there will be 2 states, and for one you will come back to non-final, for another one you will have to go to final. If that being the case, you will have to separate this, meaning this partition will be further split into 2 more sub-partitions. Like this we continue the process until, if you look at any state, for each of them the transition is uniquely defined. If that's the case, we stop our procedure. Fine. So let's look at an example, and through that we experiment this approach so that you get to understand what exactly this method is and how exactly it builds a minimum DFA through this procedure. Consider the language set of strings over 0, 1 ending with a 1. We know that the base string is 1, and after reading a 1, you can read any number of 1s. You still respect this pattern. To begin with, you read any number of zeros. When you are at this state, when you read a 0, you the pattern is lost, you will have to come back to this state and read a 1. And base string is 1, which means you need 2 states. We have completed all other transitions with the help of just this. Okay. But one can also construct, so intuitively we think this is minimum because for this we need 2, anything below it is not possible. But for the same one can also construct the following deterministic mission. Please note, for each of them, transitions are unique, meaning 0 it is Q0, 1 it is Q1, and with respect to Q1, 0 is this, 1 is this. There is no transition that says on reading a 0, you go to more than one state. So what we can do is the following. On reading a 0, what is that we can do? On reading a 1, what is that we can do? What I do, when I read a 1, I come to this state. Let me call this one as Q1. And when I read a 0, I go to this state, say Q2. Okay. Then after reading this, I may get another 1. That is also a valid string. So I go to say something called Q3. Okay. And after reading a 0, you may get a 1. So you come over here. After reading a 0, one can read any number of zeros. So we stay and read this. Okay, so now I am at Q3. I can continue to read any number of 1s. And at Q1, I read a 0, which means we lose that pattern. We need to get back, which means go to Q0 and do this. Now, when I'm here, I read a 0. Again, the pattern is lost. We go here and do this. Now it accepts 1. It accepts 0, 1, and it accepts 1, 1. 1, 0 it cannot accept. If it reads 1, 0, then you may have to read some more zeros or maybe a 1. If you want to read some more zeros followed by a 1, then take this, or you want to read a 1 immediately, then take this branch. Similarly, 1, 1 is valid. After 1, 1, you may read sequence of 1s, or you may want to read a 0. The moment you read a 0, you go back. You may read a couple of more zeros, or you read a 1 and come over here. Fine. Now let's employ the procedure what we have outlined. So initially we have P0. P0 is our initial partition. So initial partition consists of 2 blocks, namely non-final states Q0, Q2, and final states Q1, Q3. Okay. Next, what we will do, we want to know whether this will be our ultimate DFA, meaning this will become one, this will become another. What am I saying? So Q0, Q2 will be one state, and Q1, Q3 will be another state. So now let's see whether will this become our ultimate DFA. So let's look at delta of Q0 comma 0, delta of Q2 comma 0. Q0 comma 0 says Q2, Q2 comma 0 says Q2, which means when we read a 0, we stay in this block itself because Q2 is present here. Next, let us look at Q0 comma 1 and delta of Q2 comma 1. Q0 comma 1 as Q1, Q2 comma 1 as Q1, which means when we read a 1, we go to the other block as Q1, Q3 in it. Now with respect to this, 0 and 1 is defined. Let's look at this. Now delta of Q1 comma 0, delta of Q3 comma 0. Q1 comma 0 says Q0, Q3 comma 0 says Q0, which means both of them will come over here. Then let's look at Q1 comma 1 and delta of Q3 comma 1. Q1 comma 1 says Q3 and Q3 comma 1 says Q3, which means on reading a 1 we stay here. Now if you look at this automaton, you clearly see that for this state 0 is uniquely defined, 1 is uniquely defined. For this 0 is uniquely defined, 1 is uniquely defined. And since Q1 is our final state, the block that contains Q1 or the state that has Q1 in it, that will become the final state. Since Q0 is our start state, then the block containing Q0 will be our start state, and in this Q1 and Q3 are final states. Therefore, this block becomes our final state here. Okay. So, whichever block is containing at least one final state, that block will be made the final state in our ultimate DFA. So now you see that a 4-state DFA is reduced to a 2-state DFA, and we cannot have just one partition containing final states because there are non-final states here. In case all of them are final, then we can start with one state deterministic finite automaton and see whether that will be indeed minimum. And yes, it will be, because all are final states. And after that, the moment you find at least one non-final state, which means the initial partition itself will have two blocks in it. And finally, what will happen? Each block will be treated as one subset or one state. This is what we do when we look at subset construction, right? Here is a state containing subset, and here is a state containing a subset. On the similar line, state containing one block, state containing another block. So we don't need to split this any further. So this is our ultimate DFA, or this is our minimum DFA. Why it is minimum? We need at least two blocks because there are non-final states here. And with two, we are able to justify that it is indeed respecting deterministic property. So you don't need to go any further. So stop your procedure. You get to see a deterministic DFA. Okay, so what is this telling us? Now we should slowly formalize things so that it works for any example. It tells you that when you read a 0, you go here. When you read a 1, you stay here. Which means the output Q1, 1 and Q3, 1 both are coming to the same block. So similarly, Q1, 0 and Q3, 0 both are going to the same block, and they are not in some sense they are not distinguishable. On the similar line, let me use ND for non-distinguishable, and similarly these two are not distinguishable. These two states are not distinguishable. And when do you say it is distinguishable? One will go to a block B1 and this transition will go to some other block, say B2. So if the transitions are moving to two different blocks BA and BJ, then you see that they are distinguishable, otherwise they are not. On the similar line, you see that for these two it is not distinguishable, for these two it is not distinguishable. So we will formally define what do you mean by distinguishable, not distinguishable. For the time being, for this example, you see that with respect to 0, both are directed to same block. Both are directed to same block. If it is directed to same block, then those two transitions are not distinguishable, which means these two states are not distinguishable with respect to the input 1. These two states are not distinguishable with respect to the input 0. Okay, and the notion or the idea distinguishability or not distinguishability is kind of used as a mathematical invariant in proving the correctness of this algorithm or approach. Let's look at a couple of more case studies to understand this procedure in a detailed manner.